Hi everyone, this week's lab is on the synthesis of nylon. Nylon was invented back in the early 30s at DuPont. Of course, we know a lot of nylon winds up in clothes. It's also used in rope tents and toothbrushes. It's used to make belts for tires, not mainly for passenger cars, but in aircraft, trucks, and off-road vehicles. We see nylon in our cars in the belts that you find under the hood. Importantly, nylon is a polymer, and polymers are made up of many repeating molecular units called monomers. And they're linked by addition to each other, and you see them here as A as for each monomer. You can have A's all the same or different. You can have branches, etc. and so on. There are an infinite number of combinations to make polymers. Nylon is made up of two different monomers, as we'll see. There are lots of polymers around us that you are aware of course. They've had a huge impact on society, and interestingly, many are replacing metals and are being used to make advanced materials. In our lab, we're going to make nylon 610, and nylons are polyamides. Okay, now this reaction is an addition elimination reaction where you're adding an amine to an acid chloride. Okay, and this reaction is done in a biphasic solvent system. Think about why that is. We're going to have our acid chloride in the organic layer. Why would it be important to have the acid chloride in the organic layer away from water? Under the conditions that you're doing this reaction, you would get a very poor yield and probably not get any nylon at all if the acid chloride were exposed to the water for any good amount of time. So think about why that is. What would happen if the acid chloride were exposed to water and reacted with it? What would you get, and why would that hinder this reaction? There are many important polyamides found in nature. You should be able to name a few naturally occurring polyamides. Okay, what are the starting materials that you would use to make nylon 6,6 as opposed here to nylon 6,10? Now the 6 and the 10 come from, first of all, the first number there, the 6, comes from the number of methylene units, or the number of carbons in between the diamine monomer, and the 10 comes from the total number of carbons from the acid or acid chloride monomer. Okay, so nylon 6,6 would simply be the same diamine that we see with the 6 carbons, and the acid chloride would, instead of having 10 carbons, is going to of course have 6. Speaking of which, here is nylon 6,6, and this figure illustrates why nylon, the nylon polymeric chains, line up in an orderly fashion to form fibers, strong fibers. They're linked, the chains are cross-linked through, as you can see, hydrogen bonding. And it's the hydrogen bonding that gives nylons their orderly structures and strength, and interchain hydrogen bonding is very important both in man-made as well as naturally occurring biopolymers. The structure shown here, the polyamide shown here, is a relative of nylon. This is an aromatic version called Kevlar, which you've probably heard of. It's 5 times stronger than steel on an equal weight basis. Why would you expect it to have better thermal and mechanical properties than aliphatic nylons? What else is going on here apart from hydrogen bonding? And try and draw, you should be able to draw the monomers that are used to synthesize Kevlar. Propose a synthesis of Kevlar. Okay, those are some high points, some highlights of this week's lab, where you're going to be making nylon 610, and good luck.